Welcome back. We have already discussed the basic aspects and different types of modulation techniques in our previous discussion. Today, we will like to extend our knowledge on a particular type of modulation technique which we have already mentioned in the previous lecture, that is, amplitude modulation, or in short, AM. A quick recap on the members of this esteemed family, amplitude modulation. First of all, double sideband modulation. We generally call it as DSB. It can be further divided into three categories, which are double sideband with carrier, or in short DSB-WC or DSB-C. Then double sideband suppressed carrier, DSB-SC, and double sideband reduced carrier, or DSB-RC. We will confine our discussions in DSB-C and DSB-SC in this course. Then comes single sideband modulation, or SSB. SSB can also be classified into two types like DSB. SSB with carrier, or SSB-WC, and SSB suppressed carrier, SSB-SC. The other two types of AM, which we will not cover in details in this course, are vestigial sideband modulation, or VSB, and quadrature amplitude modulation, or QAM. I know the names might seem a bit intimidating at first, but as we will talk about them in details, things will start making more sense. We are starting our discussion on DSB-C. Let's start with the formal definition of modulation. Of course, by this time, you have got some vague ideas about it. Some words like carrier signal, message signal have popped up here and there. Basically, in the modulation process, there are two signals involved. One is message signal, which is the information bearing signal that we want to transmit and receive, such as raw audio, image, text, etc. This is the baseband signal we have talked about previously and mostly contains low frequency components. Another important signal involved in the modulation process is the carrier signal. As the name suggests, this high frequency signal carries the message with it. Just one other thing to mention here. A signal has three determining properties. They are its amplitude, frequency, and the phase angle. Consider a sine wave. It has an amplitude, a frequency, and maybe a phase. If you change any of these three properties, you are basically changing the signal. Now we are ready to define modulation process. Modulation process is changing or adjusting one or more of these three properties of high frequency carrier signal according to the message. So when we are talking about amplitude modulation, we will actually change the amplitude of the carrier signal according to the message signal. When the message will have low values, carrier will have low amplitude, and when message will have high values, carrier will have high amplitude. Okay. Now, here you can see a carrier signal is denoted by CT, whose amplitude is AC and frequency is FC. This is a periodic cause wave. We typically use cause or sine wave as carriers, and message can be any signal. Let's consider this message signal empty. If we are modulating this message signal with this carrier CT, the amplitude of the CT should vary with the message, right? You can see this effect if you look at the equation of the AM signal. Its amplitude is AC plus MT. As MT varies with time, the amplitude of this AM signal also varies with time. One thing to notice here is the frequency of the AM wave, which is omega C or FC, is unchanged as it was in the carrier. We can break this signal down into two parts. One is AC cos omega CT and other one is MT cos omega CT. Obviously, the first portion is the carrier itself, AC cos omega CT, and doesn't contain any part of the message. second part, on the other hand, has MT in it. Basically, this is a cause wave which is changing its amplitude according to the message. This portion is called modulated carrier. This form of amplitude modulation is called double sideband with carrier. Why it is called DSB will be explained in a moment. But now we know that why it is called with carrier, because the AM signal contains the important modulated carrier along with the carrier itself. We can also take the AC common from both the parts, and the equation now looks like this, which is 1 plus Ka into MT multiplied by Ct. Here K is called amplitude sensitivity, which is also 1 by AC. Now let's analyze these signals in frequency domain. I hope you have got your concepts of Fourier transform reviewed. Otherwise, I would suggest you to review the concepts once again. Okay, now consider this arbitrary signal we were using in the previous slide as message. Let's imagine this is the Fourier transform of this signal. Of course, these are just arbitrary shapes used for explaining purpose. You may encounter other shapes for practical signals. Just to remind you, a cause or sine wave in time domain, when transformed to frequency domain, contains of two impulses at the positive and the negative values of the corresponding frequency of the wave. This concept may come handy later. Now remember, the AM signal in time domain, it contains of two parts. One is simply the carrier signal, which has an amplitude of AC and frequency of omega c, which is actually 2 pi into fc. Another part is the modulated carrier, or the multiplication of MT and cos omega ct. As you know from the properties of Fourier transform, to obtain the frequency spectrum of this signal, we have to individually add the Fourier transforms of these two signals. Now, what is the Fourier transform of AC cos omega ct? Simply, it will consist of two impulses at omega c and minus omega c, whose amplitude are pi into AC. Here you can see that. Two impulses at omega c and minus omega c, and the amplitude is pi into AC. One thing to note here, this delta omega minus omega c means you are right shifting an impulse by omega c in omega domain. Similarly, and delta omega plus omega c means you are left shifting an impulse by omega c in omega domain. The next part is interesting. This has a signal MT multiplied with cos omega ct. Now, if a signal is multiplied by cos wave of particular frequency, in frequency domain, the original spectrum of MT, which is denoted by m omega, gets shifted to omega c and minus omega c. Previously, the center frequency was 0. After modulation, the spectrum is divided into two alike portions and the center frequency shifted to omega c and minus omega c. You can see the amplitude of each of the portion is half, because the power must be conserved. Total power in m omega is now distributed into two parts. Now let's review this whole spectrum once again and see what does this mean. We have to remember one thing, that the original spectrum of the message signal was like this. As you all know, the frequency spectrum of any physically realizable real signal is symmetric like this. It has symmetric portions in positive frequency and negative frequency. This is actually drawn in omega domain, so you can see the signal is spread up to 2 pi b, so the bandwidth is actually b hertz. Now, this is the equation of the frequency spectrum of the AM signal. You can see this has two impulses which comes from AC cos omega ct. These impulses are at two locations. One is at omega c, another one is at minus omega c. I have already explained how this is in omega c and this is in minus omega c, but for your convenience, let me recap this once again. if you draw an impulse, naturally we draw the impulse at 0 position, right? We can draw an impulse here at 0 position. But now you are shifting that impulse by omega c in the right direction. So this impulse at 0 will now get shifted to omega c. Here you can see an impulse omega c, and the height is actually pi ac. Pi ac. Same thing happens for another impulse which is shifted to the left side by omega c, and now the impulse is at minus omega c, and the height is also again pi ac. Now this image is drawn in omega domain, so their height is pi ac. But if you draw the same image in frequency domain, then the heights will be divided by 2 pi, and pi ac by 2 pi is actually ac by 2. So you can see that if we rewrite the signal in frequency domain, then the height of the impulses are ac by 2. So these two impulses here denotes that the modulated signal has the carrier component in it. Now the second portion, half of m omega minus omega c plus m omega plus omega c, comes from the message multiplied by cos omega c. As I have already mentioned, this is the original spectrum. This whole thing in the positive portion and negative portion totally forms the spectrum of the message, and the center frequency is actually in 0. Now when you are modulating with cos wave, this whole spectrum is now shifted by omega c in the right direction. You can see that m omega minus omega c. So the whole spectrum now gets shifted from 0 center frequency to omega c center frequency. Here you can see the same two shapes, same two trapezoidal shapes are distributed around omega c frequency, right? Previously this was at 2 pi b, and this point was at minus 2 pi b. Now as the whole spectrum is now shifted to omega c, this value has now become omega c plus 2 pi b, and this value has now become omega c minus 2 pi b. Similar thing happens, and spectrum is now shifted again to the left direction by omega c. So now the center frequency will be minus omega c, and again you can see that two trapezoidal shapes like the original spectrum are now distributed around minus omega c, and again this is minus omega c plus 2 pi b and minus omega c minus 2 pi b. Minus is taken common, so it is written as minus omega c minus 2 pi b and minus omega c plus 2 pi b. Okay, so these two impulses are corresponded with these two impulses here, and this m omega minus omega c is actually these two trapezoidal shapes, and these two trapezoidal shapes correspond to m omega plus omega c. Now one thing to mention, these are just arbitrary spectrum. If you take a triangle shape here, you will get a triangle here and also a triangle here. But one thing to remember is, if the original height of this spectrum is 1, then the height of these spectrums will be half. If the height of this spectrum is, let's say, an arbitrary value a, then the height of these trapezoidals are a by 2, because as I said, the power needs to be conserved. So previously, if the bandwidth was just b, b hertz, or in omega domain 2 pi b, now the bandwidth is double of that. In omega domain, now the bandwidth is actually 4 pi b, because it is ranging from omega c minus 2 pi b to omega c plus 2 pi. So the whole range is 4 pi b. So in frequency domain, the message bandwidth is b hertz and the AM signal bandwidth is 2b hertz. This is where we end our first discussion on DSBC. This is a lot to digest. I hope you will understand by going over the videos a couple of times. If you still have any confusion, please don't hesitate to post it in the discussion or email me. Thank you.